Hey everyone, in this video we're going to go over section 3.8, exponential growth and decay. In this section we're largely going to be talking about quantities that grow or decay, get bigger or get smaller at a rate that's proportional to their size. So for example, you can think of how fast a population grows is going to be proportional to how big the population is. Similarly, but in the opposite direction, if we have some radioactive isotope or some radioactive substance, the rate at which it decays is going to be proportional to the mass of that object. So in general, if we have some function y of t, and if we know that the rate at which y of t is changing is proportional to its size or proportional to its value, then we get the equation dy dt is equal to ky. Or the change in y with respect to t is proportional to its value at some time t. So when k is positive, we call this the law of natural growth. When k is negative, we call this the law of natural decay. Either way, this is what we call a differential equation. This could also get written as y prime is equal to ky. This is a little bit more common from what I've seen in a differential equation class. But differential equations are just when we can express the value of the derivative or multiple derivatives of some function in terms of constants times that function, the adding and subtracting of derivatives together. You guys will have a lot more practice in differential equations. A lot of you will probably wind up taking a class in differential equations. But for now, we just call this a differential equation. Call it a differential equation because there's derivatives inside of this equation. Let's see. So, and notice that any function of the form y of t is equal to c e to the k t. When we take the derivative, y prime is equal to, we'll get c, and then we're just taking the derivative of e to the kt with regards to t. We'll bring that k down, and we get an e to the kt, which, I'm just going to rewrite this. This is going to be k times c e to the kt, which is k times y of t. So, you guys will have the joy of going through the experience of realizing or learning that only functions of this form satisfy differential equations of that form. So we're going to go and include all that in a theorem. What our theorem says is the only solutions of the differential equation dy dt is equal to kt are the exponential, we'll say are exponentials of the form y of t is equal to y of 0 e to the k t. Perfect. So let's talk about where this y of 0 comes from. 1 second. So if you look back up here at our beginning, when I said only solutions are of that form, well, let's see what happens up here if we let t be equal to 0. That says that y of 0 is equal to c e to the k times 0. Well, k times 0 is 0, e to the 0 is 1, and this is equal to c. So what we have here is we have just replaced c, like what I had over here, with y of 0. This is just more common notation. It makes sense if we're going to be, say, modeling population like we will be doing in the next example. You have to have some sort of initial condition. You have to know how big your population is at some point. So that's why they'll go through and replace this constant with y of 0. You need to know some information about the population before you try and model it. So let's move on to our first example. So example 1 is talking about population growth. And like I said, population grows as a function of time. And if we know that the rate the population is growing is proportional to the size of the population at some time, we know that the change in population with respect to time is equal to some constant times the population at some time. So what we get over here is if we want to solve for k, we can divide both sides by p, or multiply both sides by 1 over p, and we get k is equal to 1 over p times dp over dt. And so what we do is we call this quantity the relative growth rate. The relative growth rate. And we'll use that term in the upcoming example. So, for example 1, it says, let me draw a line so I can write some stuff down. Use the fact that the world population was 2,560 million in 1950, and 3,040 million in 1960. To model the population of the world in the second half of the 20th century. To model population in second half of 20th century. Assume that the growth rate is proportional to the population size. We need that for the setup of the problem. What is the relative growth rate? We'll answer that. What is the relative growth rate? And then the second thing we'll do is we will use the model to estimate the world population. Estimate the world population in what year? 1993 and 2020. 2020. Cool, so there's a couple things to this problem that we have to discuss. Well, first off, we know, and I'm going to go on the back side, we know that solutions to equations of this form, dp over dt are equal to kp, are going to be of the form, this is going to be population at time is equal to p of 0 e to the k t. And so we want to get some information about initial conditions. Info about initial conditions. And so what do I mean about information about initial conditions? Well, our model starts in 1950. So 1950 is going to correspond with t equaling 0. That's when our model starts. That's our earliest data point. So we know that p of 0 is going to be equal to, well, p of 0 is, and I gotta find the number, 2,560 million. So we would get is equal to p of 0 e to the k times 0. Like before, that's going to be equal to 0, so this is going to be equal to 1. And we were told that is 2,560 million. I'm not going to factor the million in. We will keep it as a unit and have it kind of tag along for the ride. So what this statement says is p of 0 is 2,560. So we know that our differential equation, our solution, not our differential equation, I'm sorry, the differential equation we're trying to solve is dy of dt is equal to kt. And we know our solution to the differential equation is going to be p of t, which is equal to our initial condition, 2560 e to the k t. Perfect. In this equation, we have two unknown unknowns and we have one known unknown. That's kind of a clunky way of saying that we have to discover this value and we have to discover this value before this model will be of any use to us. So we have figured out what p of 0 is. Our initial condition says that at time 0 there were 2,560 million people. So when t is equal to 0, we get this. The next bit of information we have is that in 1960, there were, I gotta find it in my notes, 3,040 million people. So, with this information, if 1950 is t is equal to 0, then 1960, well that's 10 years later. That means t has to be equal to 10. And we know that p of 10 is going to be equal to 2,560 e to the k times 10. What we're trying to do now is we're trying to solve for k. And this is going to be equal to that number, 3,040 million. Well, solving for k, let's get the e to the 10k by itself. We can divide both sides of this equation by 2,506. 2,506. 60, I'm sorry. I should have wrote that number. Well, we will make that a 6, and that a 0. And that a 6, and that a 0. And so that already kind of looked like a 6, and that really looks like a 0. So we get e to the 10k being equal to 3,040 over 2,560. I'm sorry. And then we need to get this exponent down. Let's take a natural log of both sides. So we get the natural log of e to the 10k is equal to the natural log of 3,040 divided by 2,560. I even said it right that time. Exponents can be brought down as coefficients, and the natural log of e is equal to 1. So we get that 10 times k is equal to the natural log of 3,040 all over 2,560. I'm getting there. We want to solve for k. K is 1/10 of that value. Which is approximately equal to 0.017. Perfect. So what we have is a full sheet of paper. What we have is that our model, P of t, I can write it over here. We'll need it. That P of t is equal to 2560. E to the k is 0.017 t. And before I go on, I would recommend you guys do the algebra to this point and then plug all of this into your calculator at once. But what you're going to see here in a bit, especially when we're talking about when we're talking about carbon dating objects, the value of t, because we're going to be trying to date things that are thousands of years old. If you figure out what this is to a couple decimal places and plug it into here and figure out what that is to a couple decimal places and then divide by 10, that round off error might be large enough that it could impact your calculations. You guys all should have, I know you guys all have access to a calculator that you can plug this thing into, because you all have access to Google, and you can just Google natural log of that divided by 10 and it'll give you a value like this. So do not get a decimal, and then get a decimal. Solve for this value symbolically first and then plug it all into a calculator at once. Because like I said, for what we're doing, 0.016 or 0.018 could give you a radically different value, especially if we wanted to use our model to, say, predict the population of the world in the year 3000 or 4000. How far off that number is will be magnified depending on how big that number is. But now that we have that out of the way, we can actually solve our two questions. The first question was, what is the relative growth rate? Well, what we found out was we know that 1 over p dp dt is equal to k. And we found out that k is approximately 0.017. And so what does that mean? That means the population is increasing at a rate of about, move that 1, 2, of about 1.7% each year. And the second thing we were tasked with doing was we wanted to figure out what the population was in 1993. Okay, so if 1950 went to t is equal to 0, and 1960 went with t is equal to 10, that means 1993 is going to go with t is equal to 43. So we want to use our model to estimate what the population is 43 years after the initial start of our model. That would give us 2,560 e to the 0.017 times 43, which is about 5,360 million. Or about 5.3 billion according to this model. The next thing we want to do is find the population in the year 2020. So 2020 goes with t is equal to 70. 50 plus 70 is 20. Yeah. Okay. So that would be p of 70 is equal to 2,560 e to the 0.01770, which is approximately, sorry, I gotta look over here, 8 8,524 million. Perfect. So, what is the relative growth rate? Asking what the relative growth rate is you will naturally find the relative growth rate. In figuring out everything you need to plug in for this equation to get your answer, you need to know that value of k. So asking what is the relative growth rate was really the book trying to show you at what step you figure out what k is, trying to make a connection between there and there in your mind. Use the models to estimate the world population. The tricky thing here is our model started in 1950. So 1950 represented t is equal to 0. So all the other times that we used were relative to that start time. We didn't put, the year 1993 in here. It was since the start of our model. So that's something to be careful. The other thing is we know our solution has to be of this form. These problems you're going to always do, as far as I can remember, for the problems I've assigned you, your homework is going to start the same. Everything we're doing today is going to kind of look like that. Temperature is going to look a little bit different, and there's going to be one or two more steps to it. Newton's law of cooling. I think that's example 3. It could be example 2. We'll get there. It's one of the examples. You'll know it. So, all solutions of anything that looks like this. Our first step is to figure out information about our initial condition. They've got to give you some information about a starting point. And that's just to figure out this constant. Once you figure out that constant out front, they'll give you another piece of information. In this one, they told us what the population was 10 years ago. Now you're trying to solve for the other value you don't know, k. Once you have your initial condition and once you have k, you have everything you need to start making predictions using that model. So the first thing you do is you figure out your initial conditions. The second thing you do is use the second piece of information given to figure out the value of k. And the third thing you do is whatever the question is asking you to do, make predictions, analyze a chart, something like that. But you need your initial conditions, and then you need the value of k. So in example 2, we're going to talk about radioactive decay. So that's like you have some sort of isotope and it's decaying, it's emitting radiation, and the mass of that object is going to go down as a result. So what we're going to use is our decay model with the relative decay rate of being -1 over m dm dt. So this is our relative decay rate. And our relative decay rate is equal to that k that's in our equation. And the thing is, since we are decaying, we know that k is less than 0. Multiplying both sides of this equation by m, we get dm dt is equal to k times m. So, there's a thing to be aware over here. K is less than 0. So it's a negative number. This is mass. Mass always is going to be greater than, I should say, or equal to 0. So that means this right-hand side is a negative number. So you're expecting your derivative to be a negative number. For decay models, we're expecting dm dt to be less than 0. How much mass we're changing as a function of time? Well, since we're decaying, we're expecting to lose mass over time. So we'll need that. We will also need to know what a substance's half-life is. So if we've got some collection of something that's radioactive and it's emitting radiation, and let's say it has 100 grams as a mass, what the half-life is how long it takes in order for there to be half as much of it around. And as we'll see in these examples, these can be hundreds, if not thousands of years. It all depends on how radioactive this substance is. So, for example, the half-life of radium-226 266 is 1,590 years. So what that means is it'll take 1,500 and I'm writing my numbers backwards all day. 90 years for 100 grams of radium-226. Oh, I've written 226 and 266 on my page. This sample of radium, it'll take it 1,590 years for it to decay from a 100-gram sample to a 50-gram sample. So, and that's exactly the setup for this equation. A sample has a mass of 100 grams. Find the formula for the mass of the sample. Find the formula, or find a formula for the mass of the sample at time t. And then the next we will find the mass of the sample after 100 years. And lastly, we will see how long until only 30 grams remain. So, this is our setup. So, we know that, so by our theorem, we know if we've got this differential equation, oops, not KT, KM, then only solutions of the form, the mass as a function of time is equal to information about our initial condition times e to the kt. Okay, so we also know, so we're trying to figure out, there we go, information about our initial. Well, we know at the start e to the k times 0, that there's 100 grams in our sample. So what that tells us is that m of 0 is 100. So our differential equation, m of t, is equal to 100 e to the k t. And I know it looks like we had 100 grams, so we put 100 here. And I know in the previous example, that was the 2,560 number I kept writing backwards, and we stuck that out front too. Once we do Newton's heating, once we do Newton's cooling, that pattern's going to break. So I don't want you guys to think that you'll always put that number right there. With Newton stuff, the pattern's going to break. So this is what we know. And we also know this information about the half-life. Well, what the half-life says is that after e to the k, after 1,590 years, there'll be half as much of this sample around. That means there'll be 50 grams. Well, we want to solve for k. Dividing both sides by 100, that'll give us e to the 1,590k is equal to 1/2. We can take the natural log of both sides. That'll tell us that 1,590k is equal to the natural log of 1/2. Or what that'll tell us is that k is equal to the natural log of 1/2 divided by 1,590. Let me look over here real quick. And we're actually perfect. So what the book did is they actually left this alone as a number. I can go and retrieve a calculator so we can get a decimal approximation for this. But your guys' calculators should actually be strong enough to include this whole thing as an exponent. If your calculator isn't, if you got a simple calculator, then you'll want to expand it to several decimal places. I would use as many as possible, because like I said, sometimes our scale gets pretty big. But your calculators should be strong enough to handle that as an exponent. By that I mean that for a model, we can get the mass as a function of time being equal to 100 e to the k is going to be the natural log of 1/2 divided by 1,590 t. And this is all in the exponent. So this is a perfectly valid way of leaving your exponent. Like I said, this is going to be more accurate overall as compared to doing a decimal expansion down here. So if we wanted to say find the mass after 100 years, well, that means we just want to figure out what m of 100 is. That'll be 100 e to the natural log of 1/2 divided by 1,590 times 100. And that'll give us about 65. About 65. And that isn't milligrams because that's just grams. We've got about 65 grams. Perfect. So let's figure out how long it'll take for there to be 30 grams remaining. What that means is we want to figure out when 100 e to the natural log of 1/2 divided by 1,590 t is equal to 30. We want to figure out how long it takes for that thing to decay to 30 grams. Can divide both sides by 100 to get e to the natural log of 1/2 all over 1,590 is equal to 30 on 100 is 3/10. I would take the natural log of both sides to get the natural log of 1/2 all over 1,590 is equal to the natural log of 3/10. And I drop my t from there to there, so it would be right here, it would be right here. Trying to solve for this value of t, I can multiply 1590 to both sides to get the natural log of 1/2 times t is equal to 1590, natural log of 3/10, or get t is equal to 1,590, natural log of 3/10, divided by the natural log of 1/2. And this is, at this point, I would recommend you plugging everything into your calculator at once. And that will give you, sorry, I gotta look off camera, that will give you, that'll give you 2,762. 2,762, or approximately 2,762 years. Perfect. So it's very similar to our model for population. The only thing is we're going to have minus signs floating around. This model has them built into it, so you don't necessarily have to remember where the minus sign goes. What you guys need to know is that when we have the rate at which something is changing being equal or being proportional to its value, our solutions look like this. Our first step was to get information about our initial condition. Our second step was to figure out what the value of k was. In this problem, we left k alone as natural log of 1/2 over 1,590. I would always encourage you to leave your exponents alone and solve them or get a decimal approximation of them at the last step. From here, once we figured out the value of k, then we were just using our model the way or for what we intended to do. We wanted to figure out what the mass was after 100 years, and we wanted to use our model to figure out how long until the mass was a certain amount. In this case, it was 30 grams. Okay, so example 3 is Newton's law of cooling. So it says, Newton's law of cooling states that the rate of cooling in an object is proportional to the temperature difference between the object and its surroundings, provided that this difference is not too large. So what we have is the rate at which something cools off, so the change in temperature with regards to time, and big T is temp, and little t is time, is proportional to the difference between the temperature of the object and its surroundings. So we'll have this constant times T, the temperature of the object, minus the temperature of its surroundings. T sub S is ambient temperature. But this looks a little bit different than the models that we've been working with up to this point. So in order to solve this problem, we actually do a substitution. What we're going to do is we're going to come up with some equation y of t. And what y of t is, and that's time t, that's going to be equal to our temperature at some time t, that's this temperature, minus the initial temperature. And if we take the derivative of both sides with regards to t, we would get y prime of t is equal to t prime of t. Well, t prime of t is just d capital T divided by dt. Perfect. So what we're going to do is we're actually going to solve this equation. We know that the change in y with regards to t is going to be equal to some constant, and we defined t minus ts to be y of t. So to solve cooling problems, we'll solve the same equation we have been, but we're going to have to substitute back to actually answer the question we've been asking. Okay, so let me figure out over here. So a bottle of soda at room temperature, so we have soda at room temperature, 72 degrees Fahrenheit. Is placed in a refrigerator, is cooled off, is placed in a refrigerator, that is 44 degrees Fahrenheit. And then after an hour, after half an hour, there we go, after half an hour, the soda was 61 degrees Fahrenheit. Perfect. So that's our setup. We got some room temperature soda. We put it in our refrigerator, and after a half hour, the soda is 61 degrees Fahrenheit. What we want to do for this problem, the first thing is, what is the temperature of the soda after another half hour? So what is the temperature of the soda after another half hour? And how long does it take for the soda to cool to 50 degrees? Perfect. So we'll need to come up with an equation, and then we will need to model the temperature of the soda, or we'll need to come up with an equation that models the temperature of the soda with respect to time, and we will then be able to answer questions about predicting how long it'll take for the soda to reach certain temperatures. So our plan is to solve this differential equation like we have been, and we will use the solution of this differential equation to solve, or to come up with the solution to this differential equation. We know differential equations of the form dy dt being equal to ky have solutions of the form y of t is equal to y of 0 e to the k t. We got this theorem. We are guaranteed our solution looks like this. Well, we need to figure out what y of 0 is. Well, y of 0 is going to be equal to, over here, t of 0 minus t sub s. Or what it is the initial temperature of the soda minus T sub s, which is the temperature of the surroundings, the ambient temperature. The refrigerator is 44 degrees. 72 take away 44 is going to give us a 28. So we know that y of t is going to be equal to 28 e to the k t. Perfect. So next we need to figure out some information about, or we need the next step. We know that after a half hour, or that means after 30 more minutes, the temperature of the soda was some value. Well, y of 30 is going to be the same as t of 30 minus t sub s. Well, y of 30, t of 30 is going to be our 61, and that refrigerator is still 44 degrees, and that's going to give us 17. Yes, because 17 plus 44 is 61. So, with this information plugged back into here, we get y of 30, which is equal to this, but it's also equal to 28e to the 30k, plugging in 30 for t, and that has to be equal to 17. Now we can solve for k. Divide both sides by 28, and what that says is e to the 30k is equal to 17 on 28. I said 30. Take the natural log of both sides to get 30k is equal to the natural log of 17 on 28. Divide both sides by 30 to get k is equal to 1 over 30 times the natural log of 17 on 28. Perfect. So at this point, what we have figured out is that our solution, y of t, is equal to y of 0, which is going to be 28e to the 1/30th natural log of 17 over 28 t. Perfect. But we also know that that y of t is equal to t of t minus t sub s. And so now we can solve for t of t. What this equation right here says is that t of t, or the temperature, as some function of time, is going to be equal to 28e to the 1/30th natural log of 17 on 28 t plus t sub s. Plus t, and I don't want to rewrite that again, so plus t sub s would be plus 44. So this is going to be how we find well, this is our model. The next step is going to be to figure out what the temperature of the soda is 30 minutes later. And then we would just plug 30 in. We would get T of 30 is equal to 28 e to the 1/30th natural log of 17 over 28. T is 30 plus 44, which a quick bit of mental math says that's about 54.2 degrees Fahrenheit. So I want to stop here before we go on to B to go over the steps that really got us to right here in this box. If you guys can get to this box, I have no doubt you can do A and B by yourself. So, Newton's law of cooling says that the temperature, or the rate at which the temperature changes of an object, is proportional to this difference in temperature. You might hear it called the temperature differential, but the rate at which something cools is proportional to how hot it is compared to its surroundings. We're trying to find the temperature as a function of time. Little t is just time, and T sub s is our ambient temperature. We know how to solve things of this form, but not necessarily how to solve things of this form. But we made this observation. We said, look, if y of t is equal to t of t minus some constant, then they have the exact same derivative. That means if we can solve this thing, the derivative of y, then that has to be equal to this thing, the derivative of t. Okay, that's at least the framework, the background, the idea behind it. First steps first is initial conditions. We know that anything of this form has a solution of this form. That was given to us in the theorem. And I'm saying this form, where we have to figure out what this y of 0 is. Well, y of 0, by definition, is t of 0 minus t sub s. Well, t sub 0 is 72 and t sub s is 44. So we get y of 0 being equal to 28, which is where we get this equation from. At this point, we've taken care of our initial conditions. Then we have to use that second piece of information. We know after 30 minutes, we know we want to use the second bit, something about after a half hour the soda was 61. So after 30 minutes, well, y of 30 is going to be t of 30, which is going to be 61 minus 44, which is 17. What that tells us is that y of 30 is equal to 17. We can use that information to solve for k. Once we figure out what k is, we're able to plug it back into our model. Right here, y of t is equal to this thing. Now we've solved for k. But we know what y of t is. Y of t is just t of t minus t sub s. So now looking here, we move t sub s over and got t of t by itself. So we kind of solve for t in a backward sort of way. Once we get to here, then we're figuring out, then we're plugging in 30. I chose to do this problem where t is measured in minutes. There's nothing wrong with doing this process where t is measured in hours. It's just you would have put a 1/2 right here, no 1/2 right here. The values would have changed. So you'd have to keep in mind the units that you're using, but we never really determined a unit for time until this step. So this is just going to be minutes. Our answer to part B is going to be an answer in minutes. Speaking of part B, let's go on to part B. I don't have a back half, but how long does it take for the soda to cool to 50 degrees Fahrenheit? That means we want to know when 28 e to the, and then rk, and I've got to look on the back, 1/30th of the natural log of 17 on 28, 1/30th of the natural log of 17 on 28, plus 44. And that plus sign might be confusing because there's a minus sign in the differential equation. But there's a plus sign there because of us solving to get t of t. So I know personally that part always confuses me when I teach this lecture. That plus sign is there because of the way we solved for that. So what we're saying is what this means. We want to know when this thing plus 44 is equal to 50. Well, we'd try and get, we need t in there. We're just trying to solve for t the way that we have been. 28e to the 1/30th of the natural log of 17 on 28. Subtract 44 from both sides. That's got to be equal to 6. Divide 28 on both sides. 6 on 28 is 3 on 14. And we get e to the 1/30th natural log of 17 on 28. I keep on dropping my t. T is equal to 3/14. Take the natural log of both sides. 1/30th natural log of 17 on 28. T is equal to natural log of 3/14. Multiply both sides by 30, divide both sides by natural log of 17 on 28 says t is precisely 30 times the natural log of 3 on 14 divided by natural log of 17 on 28, which is approximately equal to 92.6. And these are minutes, so it takes about 1.5 hours in order for this soda in that refrigerator to cool from that temperature to that temperature. Like I said, the setup, getting to this point is the hard part of these problems because we kind of indirectly solve for the thing that we want. So be careful with these cooling problems. There's a lot of little parts going on. Okay, so example 4. A bit of refresher. Let's call A naught the amount of an initial investment. R is going to be the rate. We're going to record it as a decimal. N is going to be the number of compoundings per year. And we'll need T, which will be measured in years. So, if we wanted to invest a certain amount at a certain rate compounded a certain number of times per year, well, the value of this investment after that amount of time t would be given by this equation. So, for example, if we invested $1,000 at a rate of 6% compounded daily for 3 years, that would be given by this formula, and the value of our investment would be $1,197 and 20 cents. So we have a principal amount, we have a rate, we have a number of compoundings per year, and we have some time. But take a look at what happens if we take this formula. Let's figure out what happens if we let the number of compoundings, n, go to infinity. Well, the limit as n goes to infinity of a sub naught 1 plus r over n to the t, and we'll close that bracket. So we're going to break up this exponent. Notice that we can write nt as n divided by r times r times t. So we'll do that here. This is equal to the limit as n goes off to infinity of, big bracket, a naught times 1 plus r divided by n times, and this is going to be n divided by r oops, not there, all to the RT. Not that parenthesis, sorry. We want this exponent just to return right back to where it was. And so now, check out what happens. If I let m be equal to n divided by r, that also says that 1 over m is equal to r over n. And the limit, as n goes to infinity, is going to be equal to the limit as m goes to infinity. And that was an m. Okay, so we will do this substitution here. This is equal to a limit as m goes off to infinity of a naught times 1 plus r divided by n is 1 over m. N divided by r is m to the rt, close bracket. But the limit as m goes to infinity of 1 plus 1 over m to the m, well, that's the definition of e. So this is equal to a naught e to the rt. So, for a formula, if we want to know the value of some initial investment compounded continuously at some rate r, well, that's given by this formula. This is our compound continuously. So let's discuss the same investment. Let's figure out, instead of, and now we're going all over the place, sorry my battery died on me a moment ago, I'm frantically trying to get this last one in. Let's discuss what the value of this investment is if we compounded continuously for 3 years. Well, A of 3 years is going to be that $1,000 that we invested. E, now our rate is still 6%, so we would use 0.06 times t, which is going to be 3. This actually works out to be about $1,197.22, which is very similar to our compounded daily value. Honestly, going from continuous to going from daily to compounded continuous, you really don't get that much of a difference. You get a big gap, or you get a big increase going from quarterly to monthly, but that monthly to daily, or even that daily to continuously, is much less. But for compounded continuous, for problems where you're calculating the interest or how much an investment is worth after a certain amount of time compounded continuously, you're looking for these formulas, and you're free to just use this. For homework, go off and do 3, 7, 9, 11, 13, and 15. Alright, have a good day, everybody. Bye-bye.